All right, so the first mathematical expression that we will use for magnetism is the Biot Savart Law. And the way it is written is that, well, let's say you have a charge. So here's a charge Q. Now if this charge Q is not moving at all, then there's going to be no magnetic field. But if it is moving, so if this charge Q is moving, let's say in this direction at speed v, rather let's give it a velocity v. So I'm going to put a vector here. Then this thing would set up its own magnetic field, and we could draw that magnetic field. Or actually, maybe what I'll do is this. So then let's say at this position R, so here's another vector R, the magnetic field would have a specific direction and it would point in a specific direction. It would have a particular magnitude and so on. So we need vector R at this point. There would be some magnetic field B. And you could actually use the right-hand rule to figure out that, you know, in this case, the magnetic field would probably point somewhere like that. And then perhaps it would continue. You would get some kind of a circular loop of the magnetic field here. But anyways, so this is what you have. I'm going to add an angle here between these two vectors. So here's vector angle theta, angle between V and R. And let's state the Biot Savart law. So it says that the magnetic field produced by charge Q that moves at velocity V is mu naught over 4 pi times Q times V cross R over R cubed. So V is the velocity at which the particle moves. The particle is charge Q, has charge Q, and then R is the vector from where the particle is to the point of interest. So let's well, mu naught is a constant, so let's state that mu naught is 4 pi times 10 to the negative 7th, and this has units of Teslas times meters over amp. So these units are there just to make sure that the units work out in the equation. This is a constant that is considered one of the fundamental constants, and we don't take it apart any farther. That's it, mu naught. It's just like epsilon naught, and in a sense that it's a fundamental constant of nature. And then 4 pi is 4 pi. Q is the charge that actually is moving, and it has units of coulombs. V is the velocity vector of the charge. This is velocity of the charge. And it has to have units of meters per second. R vector. This is the vector that points from the charge to the point of interest. So this one it's a position vector, but it points from Q to whatever you want to calculate the magnetic field. To a point in space where you need to figure out what the magnetic field B is. And R has to be in units of meters, right? So the units would be meters. Now, if you go back to this equation up here, you could rewrite this. Follows mu naught over 4 pi times Q times V cross R hat, where this is a unit vector. It points in the direction of R, but it has a magnitude of 1 divided by R squared. These two equations are the same, and they are the same because vector R is the same thing as magnitude of R times R hat. So if R points from the charge all the way to the point of interest, then r hat points in the same direction, but it doesn't reach all the way to the point of interest because it has a length of 1. It has a magnitude of 1. So r hat, the magnitude of r hat is just 1. And that does it for this equation, although if you wish to calculate the magnitude of B, then you could write it as this. Mu naught over 4 pi times Q times V times the sine of the angle theta, where angle theta is the angle between V and r hat, divided by r squared. There's no need for me to write the magnitude of r hat because the magnitude of r hat is 1. Alright, so this is the Biot Savart law. Now we're going to use this equation here to solve the problem. Alright, here's the problem. And this one comes from your worksheet 1. This is the first problem on that worksheet, and then I think you have 3 more that are very similar to this one, so you should try them all. I'm going to solve this one. And soon enough you should see that these problems are not very difficult, but here's a proton, and the proton is moving at 10 meters per second in a positive x direction. So maybe what I'll add to this is the x, y, and z directions. So here's your, how should we do it? Here's your x-axis, here's your y-axis, and then here's your z-axis. On these axes here, you will have, maybe in green, you will have the a vector that points along the x-axis that is as unit of 1. This could be I hat or it could be x hat. It's frequent to see, it's common to see both of these. Here you would have k hat or z hat, and then in this direction here you would have j hat or simply y hat. And so these vectors here, they all have magnitude of 1. So I'm going to add here that I hat, the magnitude of I hat is equal to the magnitude of j hat, which is equal to the magnitude of k hat, which is all equal to 1. But I think you're familiar with this because we've done some cross products before in semester 1. So anyways, go back to the problem. Let's set up the given and then solve it. So given, what I have is a proton, and that means that I know the charge Q equals 1.6 times 10 to the minus 19th coulombs. Charge of a proton is known. It's moving at the velocity of 10 meters per second in the I hat direction. So I could write velocity vector as 10 I hat, which would be, I could write it also as 10x hat, and I could also write this as 10, 0, 0. 3 different ways, but they're all the same really. And then what I want to do is I want to find the magnitude and direction of the magnetic field. So my unknown is the magnetic field at a point 001 produced by this proton when it is at. So maybe what I need to do is draw a picture that gives me, that sort of shows me what's happening here. So here's the x-axis, here's the z-axis, and then here's the y-axis. So let's say x, y, and z. So now my charge Q, perhaps in red, is at the origin. So this is where I have my charge Q. It is at the origin. Its location is 0, 0, 0. And when this charge is at this location, and while it is moving in the positive x direction at velocity at the speed of 10 meters per second, the question is, what is the magnetic field at a point? What is the point that I need this direction magnetic at the point of 001? So here is what I want to figure out. What is the magnetic field at this point? So B equals question mark. I'm going to put this with a vector. vector hat, and the point of interest is 0, 0, 1. So what is the magnetic field at this specific point, given that there's a proton here at the origin that moves to the right with speed of 10 meters per second? Now I could use the right-hand rule to figure out the direction of the magnetic field all the way around this, because I could just use the right-hand rule and I could realize that the magnetic field points along this this line, along this circle here. So there's a circular magnetic field that points like this, that points like this. And so somewhere here at this point is going to point down. But I only need to find the magnetic field at this specific point, nowhere else. All right, so what do I need? Well, what I need is the vector r, which points from the charge to the point of interest. This is my vector r. That vector r is, well, in this specific case, this is easy, right? This is just 0, 0, 1. That's that. And so to solve the problem, what I'll do is the following. I'm going to substitute for mu naught 4 pi times 10 to the negative 7th divided by 4 pi times q, which is 1.6 times 10 to the minus 19th times v cross r. So v is 10, 0, 0. I have to cross this with 0, 0, 1, because this is the velocity vector. And then I divide this by the magnitude of the velocity, or rather the magnitude of the position, which is just 1, and I could square it or I could cube it, makes no difference. So let's say I square this. Equals, and let me just clarify this, which gives me, oh, that's not what I wanted. I wanted the red one. Which gives me that the magnitude of r is 1, which is the same thing as the magnitude of r hat. Right, so when I do all of this out, I'm going to find out that, well, this goes away, so that's good. End up with the magnetic field B equals. So what we get is 1.6 times 10 to the minus 26th, and then times, when I do this cross product, I end up with minus 10 j hat, which gives me negative 1.6 times 10 to the minus 25th j hat, and then units are Teslas, so I'll put times t, units of the magnetic field are Teslas. All right, so this would be solution. Now the magnitude of the magnetic field here would just be 1.6 times 10 to the minus 25th Teslas. And let's see, what else do I need to do there? Okay. Okay, I'm going to stop here with this problem. And I think instead of solving this little part that where it says repeat your calculations for different r and then a different r, I think instead I'm going to jump to another problem on Biot Savart Law just to point out something else, and that I think should do. Okay. So here's a different problem. It's really the same, but it has a little twist that you have to pay attention to. So it's still a proton, still at 10 meters per second in the x direction. So let's set up the given. Right, so there's a proton, therefore I know its charge q equals 1.6 times 10 to the minus 19 coulombs. It's moving in the positive x direction, so its velocity vector would still be 10 I hat, which is the same thing as 10, 0, 0. When it's in meters per second. Find the magnitude and direction, so find the magnetic field at a point, a specific point of interest. So let's draw a picture. Here's our axis. Let's say that this is the x-axis, this is the y-axis, and then this is the z-axis. Now the proton is at 100, so I'm looking at this here. Proton is at 100. That means that it's here. This is where my proton is, 0.10, comma 0. So let's put plus. How about in green? Let's put plus right here. This is where my charge is at 0.100. And then the question is, what is the magnetic field? Oh, and so it's here, but then it's also moving to the right at speed v of 10 meters per second. So this is what I have. Well, the question is, what is the magnetic field at a point? Let's see, what point are we looking at? 101. Okay, so let's see if we can find that point, 101. So here's 1 along the z-axis, that's 1. 1 second, that's not quite. Actually, so this is 1 along the z-axis, along the y-axis, and this is 1 along the x-axis. But what I want is the point that is here. 1 along the x, 1 along the z, yeah. So this is my point of interest now. I want to figure out what is the magnetic field at this point, because this point here, this is my point of interest, which is 1, 0, 1. What is the magnetic field here? And of course I could use the right-hand rule to figure out, so let me do this. I could use the right-hand rule to figure out that the magnetic field everywhere here points along this circular path. Right, comes all the way around and it just points in this direction here. So at this point it would point like that. But the question is, with what magnitude? How does it exactly point here? And I should find out that it points along the y-axis downwards, but I guess that's yet to come. So let's get rid of the circle. Okay, what I need to find out is, what is this magnetic field here? Well, I know it's going to point down because I figured this out from the right-hand rule, but I should be able to determine this direction also from directly from the equation. So I know that I should have 90 degrees here. All right, so anyways, so let's calculate the magnetic field. Go to the Biot Savart Law. So the equation is as follows: mu naught times, it's mu naught over 4 pi, and then times q times v velocity vector times r over, this is a cross product. If I use r vector and not r hat, then I need to have r cubed on the bottom. And I think this is what I'll do. I need to still determine this r vector. So r vector always, this r, that r vector, this one always points from where the charge is to my point of interest. So this is r, and the point of interest is here. I want to figure out magnetic field at this location. So, so I need that r. Well, that r is going to be so hopefully this is easy enough to see, but if you want to find a vector that points from this particular point to this particular point, then you have to subtract the vectors that point to these specific points. And so what I will have to do is this: 1, 0, 1 minus 1, 0, 0. And that will give me vector r, which points from charge q to my point of interest. And to be more precise, this will give me 0, 0, 1. And of course, r hat here is just, for the magnitude of r hat would just be 1, and note that this is also r hat. So I could use, so it doesn't really matter which equation you use. I could use this one, use mu naught over 4 pi. It doesn't matter in the sense that both of these equations will actually be the same in this specific case, because r hat and r actually have the same expression. Anyways, plugging in the numbers, we're going to have 4 pi times 10 to the minus 7th over 4 pi times q, where q in this case is 1.6 times 10 to the minus 19th times r. Ooh, this should be v. V cross R. So V, and V was here, 10, 0, 0, crossed with 0, 0, 1, and all of this divided by 1. 1 squared or cubed makes a difference. It's just by 1. So this goes, that goes, equals, we end up with something very similar, and that is 1.6 times 10 to the minus 26th. And then times, so when you do the x crossed with y, let's see, what do you get? You get minus y, so this should just be minus 10j hat, and that gives us minus 1.6 times 10 to the minus 25th Tesla's j hat. All right, and of course from here we can, so this would be the magnetic field B at this location. Note that it does point in the negative y direction, negative j, and if I want to find the magnitude of B, then I would have it just be 1.6 times 10 to the minus 25th Teslas. So the only thing that was here different that you have to watch out for is that sometimes you may need to do this. Determining this R vector is always the vector that points from the location of the charge to the point of interest where you're interested in finding out what the magnetic field is. Sometimes it's easy, sometimes it's not so easy. I mean, it's not very difficult, but at most you're going to have to subtract two vectors. All right, well, this will do for the Biot Savart law. You should look at the other problems in the worksheet and solve them. Make sure you know what you're doing. There's more about the Biot Savart law, and we'll do more with it, but this will do for now.